So I'd like to talk a little bit about the gamma distribution since we already mentioned it. And basically that's the idea about to incorporate the information about the rate variation among the sequences. For example, where the coding sequence is usually slower in evolution and intron is faster evolved. So you can put out those information onto the substitution models and to incorporate that. For example, here you can divide only by two different rate categories. One is slower, one is faster. Then it's easy to be done. But sometimes it's not that easy. Some sites can evolve very fast. Some sites could be evolve very slow. So we can put up a distribution of the rate categories and then put into calculations. And the best estimate so far is using the gamma distribution to do so. It's a very nice distribution, has a different shape according to the shape parameters. But it's time consuming, so sometimes we use the discrete gamma model to do so. I'll explain that a little bit later. The gamma distribution has a property of changing shape according to the shape parameter alpha. When the alpha is 0.1, it has a distribution like this one. It's an anti-J shape. And if the gamma is equal to 1, it's like this one. If alpha is equal to 5, it has a bell shape. If alpha is equal to 20, it has a very sharp value right here. The x-axis is the substitution rate. So, for example, if the alpha is very small, then it means that it has a lot of sites has a very slow substitution rate, and very few has a very high substitution rate. So that's when the alpha is very small. But when alpha is very large, and in this case, you have a very simple substitution rate right here. So if everything evolves at the same rate, then it means that it has a very large alpha value. But how do we decide the alpha? Almost impossible, actually. It's based on the experience and also based on the data itself. And usually it's quite kind of artificial, but this is from the real data. The estimate from nuclear genes and also from mitochondrial genes. And this is the alpha estimators right here. We can see almost every alpha we estimate from the real data is between 0 and 1.5. If we go back here, it means that it almost is like this one or something like that, which means that most of the sites are evolve slower and only a few sites evolve very fast. That's kind of real. And anyway, so sometimes we just fix the alpha or we can estimate the alpha from the data matrix itself. It can be done by the program itself. But it's still very time consuming to put into computation. So sometimes we just categorize into like 4 different categories for the gamma. It's called a discrete gamma model. So we have this distribution, but we separate the rate categories into this, and that. Only 4 different kind of things. And we can kind of use only one rate value to, for the calculation for the whole thing right here. So instead of the whole distribution, we can just use a fixed number, and the computation time is much less. So we can do that as well. It's very important to use this site variation model, and because this site partition could be used on transition transversion, on base composition or codon position partitions, or different things. And many programs can incorporate those information too, and it could be done. And gamma distribution is almost always can give you a better estimate. Again, we use the likelihood ratio test to test with gamma or without gamma, which one is better. And we just use the same data matrix, and it will give you the result that with gamma is always better than without gamma estimation for the calculation. So we can skip on that. And I'm going to skip on these amino acid models. It's basically simple idea. We can use amino acid for maximum likelihood as long as we have a better understanding about the substitution model of immunoanalysis. And the program can be used like POP, Puzzle, and Gaudi. And that's it. So maximum likelihood is better than maximum parsimony in incorporating the models, basically. It can incorporate more parameters. So that's the better one. And but the downside is that it's computationally very expensive. It takes a lot of time to do so.